Hi, my name's Jake Anderson, and I'm going to be introducing our final project for EEL 5718, Computer Communications. Our final project's about Sequoia Routing Protocol. Sequoia Routing Protocol is a routing protocol specifically designed for data center networks. You can see the reference here to the paper that we used for our project. The authors of this paper were looking for a routing protocol similar to OSPF, but specifically designed for data centers. So what is SRP? SRP is an interior routing protocol, and it's, like I said, specifically for data center. It doesn't work in a different type of topology. It's not very effective. It's a little bit different than OSPF, is that it uses a grid routing database, which I'll talk a little bit more about, and it's a fixed size database controlled by the SRP controller. SRP is a newly developed interior gateway routing protocol, again specifically designed for data center networks. So here's talking a little bit about the grid database, and there's on the right you can see some pictures of what it is. And so the way SRP works is here's the topology we're going to be using for our paper, and we're going to simulate this in NS3, and then we're going to measure as a switch or a node goes down how long it takes to reroute paths and compare that to OSPF. But here's just a basic topology of a data center network we're going to measure. You have your controller, your SRP controller up there on the top, and then your border switches, your core switches, and your top of rack switches, and your subnets. And so on the right over there, it shows the different grids for the different levels of switch for your border, your top of rack, and core switches. And it keeps track of what links are available and which ones are invalid and which ones go down. And it uses link state advertisements, same as OSPF, in order to do that and to update those route configurations. So here's the algorithm. All it does is pretty much 2 for loops to go through and measure how long it takes to go through each row and then column of the database, how much operating time. And so that's just kind of how SRP works. So how are SRP and OSPF different? So a grid database versus a link state database. The algorithm is different because they're different databases, obviously, to update. So we're going to try to measure how fast it responds to changes in the data center network, and we're going to do that using NS3, like I mentioned before. It simplifies routing configuration. This is a claim made by the authors that isn't necessarily true. There's not really a way to measure it. It depends on the size of your data center network and how many different switches you have in it. So how are we going to measure this? How are we going to measure the performance? What we're going to do is use NS3, like I said. We found some code and we've modified some code, and that way we can go through and implement this topology in NS3 as the authors have, and then add and take away switches as necessary. So generally what happens is we're going to have so many top of rack switches, and then we're going to add more to it, and then we're going to take. So first of all, we'll just have like as many as we have there, and then we're going to take out a link and measure how long it takes to converge. And so convergence time is calculated over there on the right. And so then after we measure that, we're going to do that with SRP and compare it to OSPF. And then we're going to add more top of rack switches, and then we're going to add more core switches and things like that. And so that's specifically what we're going to be measuring to see if SRP is indeed faster than OSPF. And that's what the author's claim is. So we will demonstrate that in the following section.
I'm going to talk about the NS3 simulator that we're using, and I'm also going to run a simulation of the SRP protocol with a link failure. So NS3 is a command line driven interface or command line driven program. To run a simulation, you create a script file, which is a C++ program essentially, and you make changes to the file, and then you run a build command at the command line, which also executes the script. So the script will accomplish several things. One, it'll set up the network topology that we're going to use, and it also allows event scheduling. NS3 is called a discrete event simulator, discrete network event simulator, because it allows you to set what point in time particular events will occur. So we'll schedule the start time for our applications and the stop time, and then the time at which the link, one of the nodes will go down. And then finally, we need some output data from the program. So NS3 provides several ways, three that we explored. The first, from the code that the authors of our paper generated, they used these NSLog statements. There's this particular one's NSLog info. There are several different levels of logging. So this just prints out to the terminal. The second type is a PCAP trace file. So you can generate these trace files, and then you can import that into Wireshark or view it in TCP dump and see what's going on. And then finally, one that we added for this simulation is an animation file. It'll generate an XML that can be imported into a program called NetAnim that will allow you to visualize what's going on. So this script file is going to create all the nodes that are used in the network topology. So for this simulation, we're going to have 2 border switches, 2 core switches, 4 top of rack switches, and each top of rack has 1 server attached. So the total nodes will be the sum of the core number, top of rack number, and border number. And then we also add the top of rack number, which is the servers. So the script file will set up, it'll create those nodes, and then it's going to create point-to-point links between those nodes, and then add network devices to the nodes with the point-to-point links, and then it's going to add network stacks and assign IP addresses, and then it's going to add the SRP routing, and then finally it's going to add applications. So we're going to have one application on a server that generates a UDP stream, and then we're going to have a sink on another one of the servers that will receive the data from the server that's generating the traffic. So to start off with showing the simulation, I'll set the downtime outside of the simulation run so that we can see that no packets are actually dropped. Oh, and I'll also mention the authors did go ahead and print directly to the output. So these cout statements, they're printing directly to the screen, so they bypass the logging system built into NS3. But what we're going to be interested in is the lost packets. So with the network or with the downtime set outside of the simulation run, we should have no lost packets. So I've changed this file, the script file, and saved it. And then I'm going to come over to the command line, and WAF is the build system that will build the script file, and also any changes made to NS3 itself will be built. And then after it builds it with this command run, then it's actually going to run that script file. So here's the output. Most of this is with the NSLog info command, and then this information is directly written to the screen. So lost packets, there's nothing displayed here as showing that we don't have any lost packets. So if I change the downtime back to 0.6 seconds, at 0.6 seconds one of the nodes will go down, and rerun this, and we'll see that there are actually some lost packets now. So we have 53 lost packets. And text output's okay, but it's a lot more exciting to be able to actually see what's going on. So if we come over to NetAnim, we'll load the srp demo.xml file that was generated by the simulation. So this shows the topology that we're using. Here are the 2 border switches, 2 core switches, 4 top of rack switches with a server connected to each one. And if I run this, we will see that server 0 is generating the UDP traffic, and then it's routing through core 1, and then server 1 is the sink. If I speed this up slightly, you can see a little better that server 1 is the source and server 0 is the source and server 1 is the sink. So the simulation started at 0.5 seconds. If I go ahead and speed this all the way up, we'll see that at 0.6 seconds, now we have a node failure. So SRP protocol rerouted from core 1 to core 0, and in the time that it took to make that transition, we lost 53 packets. So that's our simulation.
Okay, I'll be talking about the results and analysis of our project, and I'm going to compare on what the paper presents to us. So the first thing they did in the paper is to compute what they call the route calculation delay, and that's basically the delay that happens when a link goes down, and for OSPF they need to recalculate the shortest path first, and for SRP the grid needs to be updated. Unfortunately, that's not possible to be done on S3 because NS3 is a discrete event simulator, so every computation takes 0 time. And what the authors did is they used a real switch, which is the model is an Arista 7050S-64, and they implemented the algorithm on the switch to do the computation for both OSPF and SRP, and they sampled the values by changing the configuration. So the calculation is directly dependent on the topology. So they run multiple topologies and they save the route calculation delay to be used on NS3, which is the next step, and that's what we actually spent most of the time on. For us, we couldn't actually do this calculation since we don't have access to a real switch. So we actually tried to use the numbers that are present on the paper, although the numbers are not very clear. Everything else in regards to SPF and our SRP, when it's the parameters are either set to the same value or they are irrelevant. So the main difference in the simulation that we used is the route calculation delay. So now this is the part that we actually did, which is the NS3 simulation. So we run both SRP and OSPF, and the main number we are interested here, which is what the paper called the convergence time, which is how much time it takes to reestablish or to recalculate all the paths once a link goes down, and the formula is basically packets lost times packet size over sending rate. Packet size and send rate set to the same, so the only thing that changed here is the number of packets lost. And what we found out, I think Kevin probably showed it, is that the results depend only on the route calculation delay. And we don't have the exact numbers from the paper because it's not very clear, but it's clear that when we increase the route calculation delay, the number of packets lost increase when a link goes down. So the only thing we can actually say about our project is that yes, it's true that the longer the route calculation delay is, the longer the convergence time is going to be, and we had to assume that the route calculation delay is less on SRP than OSPF, which is what the authors showed when they ran the algorithm on the real switch. And the last thing they did was a real-world implementation, which again we are not able to do it. They actually used real switches and implemented their SRP on the switch, and they used a small network. And the results are that on a small network, SRP is as good as OSPF, and on larger networks, they expect SRP to be better, since the route calculation delay is less on SRP once the number of nodes in the network grows. So yeah, those are the basic results from our project.